Hi, everyone. My name is Yisroel Mirsky. I'm a Zuckerman Faculty Scholar at Gurion University. I'm going to present to you this new side channel attack on AI assistants. All the work in this project was done by my graduate students, Weiss, Daniel Ayzenshteyn, and Amit. So we're very familiar with all the different kinds of AI assistants out there, ChatGPT, Gemini, Microsoft Copilot, and we also are very familiar with how these AI assistants are being used in different use cases in industry. But the one that's most interesting to me is the use case of where people are asking these AI assistants, such as ChatGPT, for personal advice. So for example, medical advice. You might see somebody write, "Why do I have a rash on my back?" And hear back from ChatGPT, "Well, I'm sorry that you have a rash on your back," and then give some tips on how to take care of that. Or maybe they'll ask ChatGPT something about relationships, like, "What are the signs that my wife is having an affair?" And they'll get some kinds of tips on how to handle that situation. So, this is a, useful, and reasonable purpose for AI assistants, and we can expect to see those. But we're very concerned that what happens if these chats are released into the public? What if somebody in the internet can read those chats? This would be a huge breach of privacy. Now, fortunately, vendors such as OpenAI and Microsoft, encrypt their traffic. So technically, we can't really read what these communications are. Or can we? So let me take you all the way back to the beginning of this story. So several months ago, I was playing around with ChatGPT late at night, asking it some deep philosophical questions, such as, what if every single country in the world had ninjas except for Japan, who had the worst? Right? Very valid, good question. And as I'm looking at the text, glide across the screen, it hits me. Could it possibly be that OpenAI is sending every single word in a separate message? And could it be that those messages aren't padded, so I can count how many characters there are in every single word? If that were true, then I might be able to guess what those words are. So we open up Wireshark, take a look at the traffic, and sure enough, we see one packet for every single word sent. And the size of those packets are increasing. And if you take the delta between those packets, you find that, sure enough, you can count how many characters there are in every single word. Now, before I continue a bit further and talk about how we figured out what those words are, I need to take a bit of a technical aside and say that these aren't actually words, but rather tokens. Now, what are tokens? Tokens are the minimum size or basic size of word that a LLM uses in order to understand text and generate text. So we can see here two different ways that tokenizers, for example, OpenAI and Meta, how they parse different strings. And you can see basically it correlates one-to-one to words. In some cases, it's a bit different. So for example, Llama will split the word cream to two separate tokens. What's important to note is that these tokenizers are public knowledge. Everybody knows how these tokenizers work. You can access them, doesn't matter who the vendor is, and you can figure out this mapping. So what's the full threat model? So somebody types in some prompt into ChatGPT, that gets sent across the network as one big block of encrypted text. We can't figure out what the prompt was, but the AI assistant responds token by token by token back to the victim, and the attacker can look at those tokens and count how many characters are and try to figure out what those words were. So what's the big threat here? We could only see or try to guess what the response is. And the truth is that the responses reveal a lot about what the user is doing. So if, for example, if we see in a response, "I'm sorry to hear you have a rash," I think we can guess what the user's problem is. So this all boils down to a Wheel of Fortune kind of problem, right? I know how many words there are, I know how many characters there are, and I have to try and guess, what those words were. But it turns out this is a very hard problem because there's many different solutions to this puzzle. And when you think about, AI assistants and the responses, these puzzles can be extremely hard because, the response could be whole entire paragraphs of text with hundreds of words. So how did we solve this? So we turned to the, age-old solution, which is AI, and we looked towards the task of translation. Instead of translating from, say, French to English, we're going to translate from token-length sequences to plaintext English. And to accomplish this, we're going to use the state-of-the-art language model, an LLM, a large language model, to perform this task. So this is how the entire model execution looks like. The attacker sees encrypted traffic, extracts the token lengths from there, sends it to the attack model, and generates a potential solution. Now, of course, there's many ways to solve this puzzle. So we're using a generative AI here, so we just run the generative AI over and over and over again, thousands of times, to get many potential solutions to that puzzle. We then ask the AI to rate those solutions according to its confidence, and typically, or more often than not, the very top confidence result happens to be the correct solution. So let's talk a little bit more about the model itself. Now, as it turns out, if you take one big block of text or one massive long token sequence and you send it to an LLM, it's not going to do very well. It just doesn't have enough context. But we had a very interesting observation. And when you look at the responses from AI Assistant, typically the very first sentence reveals everything about the response, right? So if we look at this example here, it starts with supporting a friend with depression involves being present and understanding. Right, so we understand that this response, just from the first sentence, has to do with depression and giving support. Knowing this context gives us a lot of information about how to infer the rest of the sentences in this response. So having this insight, we go to a divide and conquer type of solution, and we say, okay, so given one big response, let's split it up into different separate sentences. Let's put all our effort into trying to crack that first sentence. And once we've figured out what that first sentence is, we can then pass along that contextual information and try and solve the subsequent sentences. But hold on a second, all the traffic is encrypted. So how on earth do I know where the sentences are? So as it turns out, when we look at all the different tokens there are and their lengths, there's only one kind of token that has a length of 1, and that's punctuation marks. Even the word "a" is 2 tokens because it's followed by a space. So all we have to do is look at that token length sequence and parse it according to the ones. And of course, we can use some heuristics to try and guess where the commas are because sentences shouldn't be too small. So this is the overall model. It's actually made up of 2 separate models, Model A and Model B. Model A's job is to be fine-tuned to solve the first sentence. Okay, so it's an expert at figuring out what that first sentence is. And the reason we just focus on the first sentence is because it has a very specific and obvious kind of pattern and style to it, which we'll talk about a bit in a moment. Then we have Model B, which is trained on all the inner sentences. We first pass the first segment to Model A, and it makes a prediction. And then we pass the second segment to Model B, and it makes its prediction, but it also uses the context of what was our first prediction for the first sentence. So it's looking at this segment, but it also knows, or assumes it knows, what the first or previous sentence was, and it makes its prediction. And we continue on this pattern throughout the entire sequence until we figured out the entire paragraph. So this works okay. We get about a 10% attack success rate, which is so-so, but we can improve it even further. So it turns out that, as I said, AI assistants, they don't just respond with arbitrary text. They have a particular speaking style, right? If you ever use ChatGPT, you'll see the first sentence often like, sure, here's a recipe for tomato soup, or whatever it is, right? So it turns out we can actually perform a kind of a known plaintext attack. If we go to our target AI assistant or vendor, such as ChatGPT, Microsoft Copilot, whatever it is, and we send it lots and lots of prompts, we can create our own data set of responses and then fine-tune our model or train our model on those responses and give it much, much better chances at figuring out or identifying those patterns in the blanks. And this works out very well. We actually get something around a 53% attack success rate. So let's talk a little bit about results. There's a lot more results. I'm not going to show all of them. Feel free, please, to take a look at our paper. And we're just going to look at OpenAI and ChatGPT-4. So here are some examples of successes when trying to figure out the first sentence. So you can see sometimes we succeed, sometimes we fail miserably. And I just want to draw your attention to some cases of the failures. For example, down here in the corner. So the ground truth was, yes, there are several important legal considerations that couples should be aware of when considering a divorce. And we inferred it as, yes, there are several potential legal considerations that someone should be aware of when considering a divorce. So although we get some words wrong, it's important to note that we still figured out very clearly what this user is talking about, and that is a huge breach of privacy. So it's not all about, accuracy of words, but more about the sentiment analysis. You can take a look at our paper, how we measure that. We use sentence transformers and so on. And if we look at trying to predict entire paragraphs, we get about 38% attack success rate, which is also quite nice. Another consideration is, of course, we're talking about network traffic, and there sometimes can be queuing and buffering that happens on the service side. And as it turns out, we did an analysis over 24 hours, and we know that sometimes some tokens get grouped together. And when they get grouped together, it might be hard to try and figure out what those words were. So what we did was we went to our data set, and we just augmented it. We just did random groupings of tokens, and we trained our model on this augmented data set to try and see if we can look past this noise. And it did quite well, and with this augmentation, we still got about a 35 to 50% attack success rate. Okay, so a little bit on the disclosures and defenses. So around February 2024, we disclosed this to all the affected vendors, which was pretty much every single AI vendor out there except for Google Gemini, because they respond their responses are in batches. And after this disclosure, it took them about 1 month to patch it. We were talking to their engineers, which is actually quite fast. And they gave us quite a few bug bounties, which was nice. And then we had a public release a few weeks later in the middle of March. So when we're working with the engineers, basically the solution is very straightforward. One thing you can do is just add random padding to every packet. You can pad to the nearest. You can group tokens together. And this is the general mapping of how those vendors decide to solve this problem. Okay, so to conclude, so the main contributions of this work are twofold. First of all, we discovered a novel side channel attack, which we call the token length side channel, which affects many different LLM services. And the second contribution is that we've shown that you can use generative AI to directly exploit a side channel, and specifically this side channel, to infer what is actually being sent across that communication channel. And it works so well that we're able to infer in many cases, paragraph level inference. And we've also shown a nice way of performing a known plaintext attack by training our model on examples from our target. And two main takeaways here are, number one, make sure you use encryption schemes correctly. And even though many vendors are trying to get on the AI gold rush, you have to be aware of that. You have to think about security by design and slow down for a moment, think about the communication as a whole and not to fall into these traps. And number two, AI is your friend, right? So when it comes to breaking side channels, paragraph level inference was something considered very, very hard, but now it's possible, especially with these large language models. And that also begs a much bigger question as to what other side channels out there can be exploited by generative AI. And one last thing is we have our tool up on GitHub, so feel free to download it, play around with it. You can train your own models, you can execute it yourself. It supports token length sequences, so it doesn't go from the raw traffic. You'll have to give it the token length sequences. And we provide some models and assets there for you to get started. And that's it. And if anybody has questions, I'll be happy to answer.